Hi, everyone, and welcome to SQL Bits 2020. And welcome to this session. If you're a SQL Server DBA and you want to learn how to deploy, run a SQL Server database off of a Docker container, this session is for you. My name is Edwin Sarmiento, and I'm a Microsoft Certified Master for SQL Server and a former Microsoft Data Platform MVP. Now, this session is a snippet off of the book, The SQL Server DBA's Guide to Docker Containers. I want to start off with defining a term that's been overly used nowadays, the term DevOps. You ask a dozen people about what it is and get 12 different responses, 12 different meanings. So what I did was I took a definition off of Amazon's AWS website and highlighted key phrases and words to describe what DevOps is. DevOps is the combination of cultural philosophies, principles, practices, and tools. It's not one or the other. It's a combination of all these. The goal is to speed up delivery of applications and services. I remember about 15 years ago when I was working as a data center engineer, we were already doing DevOps without even calling it DevOps because we don't even know it was called DevOps. Our goal is to make sure that we are deploying services and applications fast. So we're automating, we're defining workflow processes. Part of our culture is to hire engineers with the same way of thinking. And this has made our processes smooth, and it's also repeatable because all we did was to define a process and find the right tools and automate this entire process. Like I said, we didn't call it DevOps because we don't even know it was called DevOps. And the goal is, again, to make sure that you're delivering services and applications fast. Docker containers is just a tool that makes up or contributes to your entire DevOps practice. But before we dive into Docker containers and how you can deploy SQL Server on Docker containers, let's go back to the days when we were trying to solve a totally different problem. Think back to the days of deploying applications on servers and physical machines. You know, what's ironic is the fact that we call ourselves data professionals, yet we were guessing. What do you mean by guessing? Well, if you want to deploy an application, a brand new application, you don't really know how much CPU, memory, or storage requirement you would need for the application. That's what I mean by guessing. So what you end up doing is you go to your purchasing department, ask the person in charge, hey, can we buy the top of the line servers from back then IBM or Dell or HPE, and then deploy your applications on those machines. 5, 10, a year down the road, your server is barely hitting 50% utilization. And your CEOs and your CTOs and CIOs are not even happy about the fact that the server is underutilized. This is where virtualization came in. With virtual machines, you can still buy the top-of-the-line machines, physical machines, install your hypervisor, and then throw in as many VMs as you possibly can on that physical machine. Now we're maximizing resources. We're maxing out the compute resource as well as the storage resources. We're no longer guessing. We could just throw as many virtual machines in there as we possibly can. Of course, that also introduces all sorts of different problems like over-provisioning of virtual machines. But when you really do think about it, the way we deploy servers and applications has completely overtaken the way we contribute to the business. IT's goal is to make sure that it contributes to the goal of the business. But when you think about it, what do we do as IT professionals? We deploy servers, we patch them, we secure them, we update them. None of these are just necessary evil in order to make the applications work. The bigger challenge there is, when you're troubleshooting a problem in production, and then you ask the developers, hey, how come this doesn't work in production? And the developers would end up saying, well, works in my laptop. That is a very frustrating thing to deal with. So when you really look at Docker containers and containers in general, you might want to ask the question, what problem does it really solve? I mentioned a few key things as an IT professional and working in operations back then about the care and feeding of operating systems and servers, instead of really focusing on the app. When you look at the developers, deploying applications should be standard across the board, and the experience of deploying an application across different environments should be uniform. Containers are meant to solve both. In fact, the biggest deal with containers is you want to reliably deploy software across different platforms. You want to make sure that your software that ran on your developer's laptop works exactly the same as when you deploy it in production. Of course, the reality is sometimes a developer's laptop is more powerful than your production servers. But that's beside the point. Let's look at the difference between containers and virtualization. Because when you do think about it, a lot of people mistake containers kind of like an evolution of virtualization. They sometimes call it virtualization 2.0. But understanding the difference between the architecture will help you distinguish which solution works for which problem. Let's look at virtualization. On the left side of the image, you see your hypervisor architecture. You get your physical machine, you install a hypervisor layer, whether it's VMware, Hyper-V, or whatever hypervisor architecture platform rather that you choose, and then you create a VM. The goal or the job of the hypervisor is to abstract the physical machine. You present the compute, the storage, and the network resource as if they were real from the point of view of the virtual machine. Once you have a virtual machine, you start installing an operating system. That is the only time that you can run an app on that particular VM. I wish we didn't have to install operating systems, but they're a necessary evil. Well, sort of. The number of virtual machines that you can run on a physical machine will depend on the physical resources that your physical machine has, storage capabilities, and the type of apps that you want to run. You can even mix and match different virtual machines running different operating systems, because what you're simply doing is you're abstracting the physical machine. In contrast, with containers, well, same thing. You have your physical machine, but instead of installing a hypervisor layer, you're installing, just like anything else, an operating system. Inside an operating system, you would then install your container service or container daemon from the point of view of a Linux operating system. The container will then abstract the operating system. Quite different from hypervisors, where the hypervisor abstracts the physical resource. The container abstracts the operating system. So instead of having multiple operating systems running on your physical machine, you're only running one operating system. Within a container, you can then run an application on top of it. Now, think of it this way. Given the storage requirements of containers, you can run as many containers as you possibly can, given the same amount of storage resources. In contrast with hypervisors, well, you have to worry about the operating system, the storage requirement for that, plus the storage requirement for the application itself. So you can run more containers on a physical machine compared to running multiple VMs on a hypervisor. But more importantly, it's the fact that I only have to deal with one operating system, which means, well, there's less management overhead. I only have to monitor one operating system. Patch, secure, update, manage one operating system versus multiple operating systems. The concept of containers came from Linux. That's why the things that I'm going to talk to you about today will focus mostly on Linux. Although Microsoft was able to come up with their own version of containers that could run Windows Server containers, the concepts were taken from Linux. What you're trying to do here is you're trying to virtualize the operating system kernel. And that's also one of the reasons why a Windows container will only run on a Windows container host. A Linux container will only run on a Linux container host. Although there are some workarounds that would make a Linux container run on a Windows host, but that's another layer of abstraction. For production environments, it's ideal to run a Linux container on a Linux Docker host, as well as a Windows container running on a Windows container host. This is also sharing the hosts kernel. You're introducing the ability to share the kernel, which means, again, instead of having multiple copies of the operating system, you only have one copy. Every container will then tap into the capabilities of the hosts kernel and present that to the container layer for the application to use. It uses the kernel's ability to group resources or processes for resource control. Think, instead of having virtual machines, think of having multiple applications running inside your operating system, and they're all isolated, which means every single application will have its own view of your compute, your storage, and your network resources. In contrast with virtual machines, it's as if you really have your own operating system within a virtual machine. And finally, like I said, most people think they're VMs because they feel like they're lightweight VMs. In reality, they're not. They're not virtual machines because, again, virtual machines abstract the physical hardware. Containers abstract the operating system. Now, how does Docker run containers? Now, when you look at this image, you see a Docker daemon. Now, a daemon is just like a service on Windows, but that's how it's called on Linux. You see a Docker daemon running on a Docker host. Your host could be a Windows machine or a Linux machine. But throughout the session, I'm going to refer to the Docker daemon running on a Linux host. Well, since containers were based off of a Linux concept. The Docker client runs a command, in this case, a Docker run command. The intent is to run a container on a Docker daemon. The first thing that the Docker daemon would do is search its local storage repository. It will search, hey, do I have a copy of this image that this client is trying to run as a container? If it doesn't exist locally in the storage subsystem, what it will do is it'll reach out to a container registry. Now, the default container registry for Docker is the Docker Hub. Think Google Play Store or Apple App Store. This is where all of the publicly available images are stored, and the Docker daemon will just reach out to the Docker Hub, search for that image, and then if the image exists in the Docker Hub, will pull that image down into its own local storage repository. Of course, pull is just a fancy term for downloading. And the Docker daemon would then store that image locally in its storage subsystem. Once that image is there, it is the only time that it will run a new container based off of that image. That container is kind of like a runtime copy of the image. Now, once that file or that image is locally available, you can run as many containers as you want from that image. It'll be quick and fast because, well, no more pulling, no more downloading from the Docker container registry or other container registry. So instantiating containers will be a lot faster the succeeding times compared to the first time you'll run it. I want to show you how this whole process works. Let's take a look at my Windows workstation here, and I'm going to use a very familiar tool that you'll get yourself using when you start working with any Linux environment, and in particular, in this case, a Linux Docker host. The tool is PuTTY. It's an SSH client that I typically use, and you're probably going to start using when you want to connect to a Linux machine. So I'm going to connect to my Linux Docker host named CentOS Docker 01. I'm going to connect to it, provide the IP connecting to a remote Linux host. I'm going to click open. Key in my credentials to log in. I want to introduce you to a very important concept in Linux, the concept of least privilege. Here I'm logged in with administrator privileges. I mean, my account has administrator privileges. But within Linux, in order for me to execute commands in administrative mode, I have to tell Linux that I need to execute those commands. In fact, if I run a simple command like docker info, it tells me I got permission denied error. And that's because, again, I need to elevate the permissions in order to execute this. The way to do this is by running the sudo command prefixed to any of your administrator commands. This just tells Linux, hey, give me elevated privileges, like sudo docker info. It'll prompt me for my password. And this command just displays the information about my Docker host. As you can see, these are some of the information about my Linux Docker host. I don't have any containers running at the moment. My operating system is running CentOS Linux 7. Got 8 gigs of RAM for this machine, and other information about my Docker host. Now, I want to show you how Docker runs containers based off the slide deck that we just seen, in the previous slide. So I want to run a very simple Docker command. It's a simple hello world container. Now the command here is, I want to run the hello world container. And this explains exactly what you saw from the previous slide. Let's have a look at what this entire command, or this command did. For one, we ran a Docker run command, meaning we're telling the Docker daemon we want to run a container. Container name, hello world, meaning it is based off of the hello world image. The line there, unable to find image hello-world latest locally, this simply means that the Docker daemon attempted to search the local storage repository, meaning its local disk subsystem, for the existence of this file or this image. It didn't find it, therefore went out to Docker Hub, pull that image from the Docker Hub. Once the entire image had been pulled, ran the container. Now, pretty obvious, the container's task is simply to display this bunch of text. In this case, it explains everything that I just explained in the previous slide. Step 1, Docker client contacted the Docker daemon, and so on and so forth. Once the Docker container has finished running whatever app it's running inside, it exits. And that's why what you see in here, once a container completed its task, exits. Now, the next time I run a Docker container, I no longer need to go to Docker Hub and pull that. In fact, what you're seeing here is the Docker Hub website or the portal. And you can search for any available image that you want to pull or use to run containers. Let's say I want to search for .NET Core based containers from Microsoft. And you can see you've got the .NET Core SDK, the .NET Core runtime, anything related to the .NET Core. This is the portal that the Docker daemon searches through the API in order to pull the images that you want to run containers off from. But SQL Server has its own section in the Docker Hub, the Microsoft SQL Server, and these contain the official images for the SQL Server on Linux or Docker engine. Here's the thing though. If I decide I want to pull a SQL Server on Linux image that I want to run off of my local Docker host, this is the default location. But if you look at the command that is provided as an example, you see Docker pull, then you have like mcr.microsoft.com. It is actually looking at the Microsoft container registry if you decide to explicitly define the container registry. So let's say I want to pull the latest SQL Server 2017 on Linux image. This is the command that I'm going to use instead of just specifying MS SQL Server -Linux. The thing about the Docker registry or the Docker hub is that you could search for images in a Docker hub. So for instance, I want to pull that specific image, SQL Server 2017 with CU16 running on Ubuntu. If I pull that image, I'm actually telling the Docker daemon to search the Microsoft container registry instead of the Docker hub. Now, if you look at what is going on here, I simply pulled the image. I didn't run the Docker run command. What this is doing is it's simply pulling or downloading the SQL Server on Linux 2017 running on Ubuntu Linux with the CU16 image. And if you see, there are like sections within the message already exists. And some of the messages there like pull complete, pull complete. I'm going to explain this a little bit in more detail in the next section as we start looking into what an image is. And there you have it. The image has now been pulled from the Microsoft container registry, stored into the local repository, the local subsystem, so that the next time I want to run a container based off of this image, there's no need to pull the image because it's already in the local storage repository. Now, if I want to search or explore all of the images that I have available, I can run the Docker images command. And you can see my hello world image, my SQL Server 2017 with CU16 image. I've also pulled the CentOS Linux image version 7.6 because I'm going to use that in the later example. And you've also seen an extra image here, the SQL Server 2017 with CU13 image. So I've got 4 images stored in my local Docker host, meaning they're all in the local disk subsystem. Now, I did mention a few terms like images and Docker and containers. I want to explain the difference between these two. What is an image and what is a container? Images are read-only templates for creating application containers. I kind of think of images in programming constructs as classes. Containers, on the other hand, are a runtime instance of an image. In programming construct, I kind of think of containers as an object. So again, in object-oriented programming, think images are classes and containers are objects. I can create multiple instances of a class or an object based on a class, and I can make modification to properties, methods, events without affecting the image. If you recall that in the example where we pulled an image from a container registry, we see an image. And that image is actually a combination of different file system layers. And when you think about file system layers, think, one file and another file stacked one on top of another. An image is a combination of file system layers and metadata that describes it. I kind of think of this as, Lego pieces. I can, let's say, buy a box from maybe the Batman Lego series, and it will come with an instruction set, an instruction manual on how to build the Lego pieces to make it look like the Batman Lego series and the different Lego pieces. Now, what I can do is, let's say I want to build a totally different Lego set, maybe the Star Wars Lego set. I can take pieces from the Batman Lego set so long as I have the instruction manual for building a Star Wars Lego set and build a totally different Lego set. What makes, of course, there might be cases where there's specific Lego pieces for Batman Lego and for Star Wars Lego. But the thing that differentiates these two will be the instruction manual. The way you build the Batman Lego set will be different from the way you build the Star Wars Lego set. Every single layer is what makes up an image. You've seen the message earlier when we are pulling the SQL Server 2017 on Ubuntu Linux image, where you have, layer already exists, and then some of the lines where it starts pulling. Now think of it this way. Every single file system layer makes up the image. Let's say, I'll just use a virtual machine as an example. Let's say you're creating a new virtual machine. That's a file. You install the operating system. That's a delta or change from the original virtual machine file. You install a service pack. That's a delta or a change from the file system layer that contains the operating system. You install SQL Server. That's another delta, which is a change from the file system layer that contains the service pack, which runs on top of the file system layer that contains the operating system, which runs on top of the file system layer that contains the virtual machine definition. So think of an image as layers of file systems stitched together. Now, of course, if I want to pull a SQL Server 2017 on Linux with CU21, if I already have an image with CU16, for instance, I already have the image layers up until CU16. The only thing that I need will be, the file system layers that differ between CU16 and CU21. Now, the metadata is the one that defines the image. Once the image has been built, this is kept as a read-only file. Once I have an image, I can now create a container based off of this image. Now, you might be wondering, wait a second. If I'm going to build a SQL Server instance and I'm going to install SQL Server and I'm going to add databases, how can I make modifications to this read-only file system layer? Quite interesting. And this is where Docker creates a read-write layer. Any change that you make in the container does not happen on the read-only layer. It happens, or it occurs, on the read-write layer. And that's why you can make, as many, or you can run as many instances of a container, each one with its own read-write file system layer, and not affect the underlying base image. Besides, it's read-only. So this is how a container runs on top of a read-only file system layer, which is the image. I may be interchanging container and image, but think an image is the base image, the read-only copy, whereas the container is the read-write file system layer that runs on top of the read-only layer. So let's try running a SQL Server container based on the image that we just pulled. I'm going to use the docker run command here, and I'll explain some of the parameters. The -e parameter is just for environment variables. This is where we tell the container any environment variables that we need to pass are in here. You're probably familiar with the accept underscore EULA because you've been reading the end user license agreement every time you install SQL Server. It says no one ever. SA underscore password is the sysadmin password that you can use so you can log into your SQL Server instance the first time. The -p parameter tells the Docker host, hey, every time you get a connection to port 1433, redirect it to port 1433 on the container. --name is the name of the container. I want to be able to identify the container that I just created in case there are other containers running on this machine. -d, I want to run it in detached mode. I want to make sure that I'm not connecting to the container directly from the terminal. It's like making it run in the background. -h, I want to name this container Linux SQL 01. -h is kind of like the host name. In case your developers hard code connection string values in their applications, and if they want it to be named like this, I want to provide it the name. Finally, I want to specify the image name. In this case, it's a SQL Server on Linux 2017 with CU13 running on Ubuntu. I want to make sure that I am using this image. Oh, and by the way, you probably noticed earlier that I've already pulled the image and stored it locally. So let's run this and create a new container. Now, before I run the command, I want to ask you this. How long does it usually take to deploy a SQL Server instance? Think back to the days of physical machines. If you have a physical machine lying around, probably a couple of hours. But if you don't have any physical machines lying around, probably a couple of weeks or months, depending on how fast your hardware vendor can sell or provide a hardware. What about virtual machines? How long does it take to deploy SQL Server instance on a VM? If you already have a VM template for Windows and just installing SQL Server, probably a couple of hours, right? Deploying the VM and then installing SQL Server on top of it before you can even have a SQL Server instance. It's roughly a couple of hours. With containers, after we pull the image, just a few seconds. In fact, the minute that you see this GUID value appear is the time when the container is already available. In fact, if you want, let's connect to SQL Server Management Studio right now, or rather to the SQL Server instance using SQL Server Management Studio to prove that it is indeed done in less than a few seconds. Didn't have to wait for hours, didn't have to wait for days. It's there. So I'm going to connect to the Linux Docker host using the IP address. Well, I don't have a DNS. So let's have a look at the password that we use to build the container and run the container for the sysadmin login and connect to it. And there you go. I was able to connect to the SQL Server instance running on a Docker container. Let's have a look at the properties. Two properties that we want to take a look at. Number one, the host name or the server name or the instance name. Linux SQL 01 is the one that we used to build a container. So you got your system databases in there, the SQL Server instance. But like I said, let's have a look at the SQL Server instance name as well as the SQL Server version based on the container that we just ran. We do select, add a server name, and add that version. And as you can see, we do have Linux SQL 01, which was the name of the container we ran. I mean, the host name that we assigned to the container when we ran it. We're seeing SQL Server 2017 with CU13 running on Ubuntu 16.04.5 Linux. I might be wondering, wait a second. I thought you were running a CentOS Linux as the Docker host. Why is it running on Ubuntu? Well, remember, containers are there to abstract the operating system, specifically the kernel. Linux, so long as you're using the Linux kernel, you're good. The only thing that will be added to the container are those that are specific to Ubuntu. So what if you want to create your own custom image? Maybe you don't want to use the publicly available images from Microsoft because they're running Ubuntu. And I'll be honest, I prefer running Red Hat Enterprise Linux or CentOS if I don't want to pay for expensive support from Red Hat. What if I want to create my own image? And this is where the Docker file comes in. What is a Docker file? A Docker file is simply a text document that contains all the commands a user could run on the command line to create a custom image. Think of the Docker file like a recipe book, right? Instead of you typing all of the commands on the command line to build an image, you write them on a Docker file. And this Docker file, well, Docker's kind of a little bit strict on the file name. It has to be named Docker file with uppercase D with no extension file name. The Docker daemon will interpret the Docker file, parse it, and then translates it and converts it into an image. Let's explore what the Docker file contains. The first line, the from command, tells the image the starting point or the base image of this custom image. In this case, we want our SQL Server on Linux image to run off of CentOS 7.6 instead of Ubuntu 16.05. The next sets of commands are just labels. They're just metadata telling other people who want to use this image to run containers off of what this is all about. Maybe the name, the version. The next two commands, run commands, is kind of like how you would install SQL Server on Linux. First run, we're telling the local Linux image to pull the Microsoft repo file for SQL Server on Linux. Repo file is just one way of telling the Linux subsystem this is where the location of SQL Server in this case and where to pull the packages from. The next run command is just telling the command or Linux, hey, install SQL Server. The env command tells or specifies environment variables. In this case, we're telling our environment variable path that this is the default location of our SQL Server binaries in Linux. The succeeding run commands, mkdir, I want to create a new directory. In chmod, I want to grant permissions, modify permissions for both group and user, meaning the MS SQL user created during installation, and I want to give them permissions to these two directories. Var up the MS SQL and etc password. These are directories that SQL Server will use as part of the installation. The expose command just tells other people who are using this image, hey, the container running off of this image will be running the application using 1433. The final command, SQL servr. This runs the SQL Server app or the application, right? It's just like running SQL Server.exe in Windows. The last command in the Docker file is what needs to run the application. To build a custom image using the Docker file, we use the Docker build command. In this case, we're specifying the tag name, and the dot is just a reference point. We're telling the Docker daemon, hey, look for the Docker file in the current folder. Now, you can manually provide the full path if you want to. I'm just lazy. I'll just create a Docker file, put in that directory, and run the Docker command from there. So I want to go back to my Linux Docker host. And I've already created a Docker file inside my home directory. I created the tmp build directory inside my home directory. I want to navigate to that, and you see a Docker file image there. If we read the Docker file, it looks exactly what you saw on the slide. So I'm just going to use this current location and run the Docker build command so that the daemon would start parsing this, evaluating, and then build a custom image using this Docker file. I'm going to run this command. Of course, prefix it with sudo. Provide my password. And off it goes. And it starts, going through every single line in the Docker file. Like in this case, it's now on step number 7 of 13. And it's already pulled the repo file, and now it's on step number 8 and starts pulling the SQL Server binaries off of the definition in the repo file, and now it's currently installing SQL Server. And there you have it. After completing all of the steps defined in the Docker file, it has built the image that we told it to build. Now let's go ahead and run a container based off of this image. You can see the command is exactly the same, except of course I'm using the image that we just built. I'm also using a different host name and a different container name, because I want to make sure that I reference the correct container. Now in this case, because we are currently running a SQL Server on Linux container, which uses 1433, I want to use a different port number this time. Second container, any connection to port 1443 on the host will be redirected to port 1433 in the container. So let's run this. And voila, it's there. Let's connect to SQL Server Management, the instance using SQL Server Management Studio to check if indeed this is the instance that we just deployed. We'll connect to port 1443. We use the sysadmin password. And there you have it. You can see that we have different version numbers, right? So let's, check the host name or the instance name as well as the version. And there you go. Linux SQL 02 is the name of the container. And look, it's running SQL Server 2017 with CU21, because I didn't specify any CU number. And it's running on CentOS Linux 7 instead of Ubuntu. So this is an example of how you can create your own Docker image and standardize deployment of your SQL Server instances. Of course, you don't want to have a different version on your production system that you're using for your development systems. You want them to be uniform or standard across the board, and this is how you standardize on creating a custom image that meets your specific business need. If you want to dive deep into this or just get through, go through learning all of this, I've written a series of articles on mssqltips.com on how to, get started, work with containers. And just to sum it all up, containers are just another tool in your entire DevOps practice. There are other tools available. What you have to keep in mind is the fact that this is just one of the 4 things that we've talked about: cultural practices, philosophies, tools, and the culture. If you want to learn more about how to deploy SQL Server on Docker containers, go grab a copy of my book, The SQL Server DBA's Guide to Docker Containers. And with that, thanks for attending my session.